Hello and welcome to this manufacturing process technology part 1 module 17. In the last module we were discussing about the simple vertical gating system, and we tried to develop an equation where you could actually estimate the time of filling of a mold of volume V by estimating again the gate velocity and having an idea of the area of the gate cross section. So, let me just delve into that a little bit just for recall sake. So, we had actually investigated this particular design right here, and we had formulated this TF value, okay, which were under certain presumptions that this was essentially based on the principles of frictionless fluid flow and the formulation came from the integrated energy balance equation. Further, an assumption was made that the pressure at which the mold is kept is atmospheric pressure. So, this led to the estimation of the TF value or the time of filling up of the mold. Let us now look into the other design, that is the bottom gating design, and try to estimate how we can apply the Bernoulli's equation in this particular case. Okay. So, let us say that in this B part of this figure, if we apply Bernoulli's equation between points 1 and 3. Okay. So, 1.1 is here, point 3 is the gate right about here. So, at 1 we get that the obviously the atmospheric pressure P atmosphere is the pressure at point 1, divide this by the density of the liquid metal times the acceleration due to gravity rho. We have a velocity head here which is completely 0. We assume that there is no velocity at the top of the pouring basin, V 0 is 0, and so this 0 is the velocity head, V square, otherwise V 1 square by 2 g. Okay. And then you have H t as the total potential head that is available at the top point 1 here of the pouring basin. So, this is the point 1, and if we do the energy balance at point 3, we have the pressure, let us say here for example, is illustrated as P 3. So, we have P 3 by rho g, which is the absolute pressure here. Okay. So, we recall that this is the absolute pressure at P 3, and obviously, the gauge pressure would be in difference to the atmospheric pressure. So, P 3 minus P atmosphere would really be the gauge pressure. I can say at point 3. Okay. So, P gauge would be the gauge pressure at point 3. So, this is P 3 by rho g plus the velocity. Let us suppose the velocity at this particular point is V 3, because the fluid is running from a certain potential, there is a change in the potential energy of the fluid because it is running from a certain height h t all the way to the datum line, which is somewhere around this corner here, right about where the V 3 is being estimated. So, the V 3 square by 2 g, and then obviously, the height from the datum line here that we consider is considered to be 0. Okay. So, really having a head loss between the point 1 and point 3 with 3 as 0 line or the datum line. So, obviously, in this particular case we just write this as rho m just to avoid the confusion. Rho m is the density of the liquid metal. So, if I now apply the same equation once again, so applying Bernoulli's equation now between 3 and 4. So, basically we have one point here, 4 right about here, and the point 3 that we have just calculated. So, we have to do an energy balance between 3 and 4, point 3 and point 4, and we assume, we make some assumptions here. One assumption is that we assume that the overall dimension of the mold is very large. So, the velocity head at 4 can be assumed to be negligible. So, obviously, the assumption may not seem to be practicable, but if you consider the fact that the area that is feeding the gate AG is too small in comparison to the overall dimension of the mold, in this case the mold height is HM and probably the diameter is probably several times, maybe hundreds of times more than the gate area. So, you can consider that for the instant of time that we are considering, the velocity or the kinetic head at 4 may be negligible, because the rate of rise because of whatever small amount of metal has entered the mold cavity may not be significant, because it is get distributed over the whole area of the mold, which is a very big number. Okay. So, we assume that to be negligible, and so we can probably also say that at 3 we assume that there is a complete kinetic energy loss due to the metal coming out. So, you can see that at this point 3, because the gate region is again too narrow and the metal is coming out into the open into a very, very large area, we can assume that this kinetic energy which was there just before the entry of the gate, and the moment it has entered the zone 3, that means it is into the mold now, and which is the zone 3 that we are considering here really. So, there the kinetic energy is completely lost to the system, or we can assume that for this particular case the energy equation would be P 3 by rho m times of G is equal to the height h. So, we are assuming V 4 to be equal to 0. We are also in a way assuming V 3 to be completely lost as the metal enters the mold. So, this is just about the same instance of time, the only thing is it has just entered the mold from the cross sectional area, and we are assuming that the amount of kinetic energy delivery to the mold is negligible in comparison to the overall mold sizes, etc. So, sorry, the kinetic energy is negligible because of the overall largeness of the mold size, etc., and it is as if that a few droplets are emanating from that small gate region into a bigger mass of fluid. Okay. So, the kinetic energy addition is very, very low, and so we are assuming this V 3 beyond the gate region to be equal to 0 for that case. Similarly, V 4 is 0, and we assume that P 3 is the gauge pressure. So, basically what we are talking about is the difference of pressure between P 3 and P at 4, where P 4 is equal to P atmospheric pressure. Okay. So, the gauge pressure is always, as you have recalled here, with respect to the atmospheric pressure. So, we can say P 3 minus P atmosphere is actually the gauge pressure here. I will call that P 3, okay, because we are now getting a baseline of P atmosphere and neglecting the P atmosphere everywhere, like just we did in the past here, where we talked about this particular equation here, H t equal to P 3 by rho m g plus V3 square by 2 g. Okay. So, from here we can probably obtain the value of P 3 to be equal to rho m g h, and if I substitute the value of P 3 in this equation right about here, we get H t equals P 3 by rho m g plus V 3 square by 2 g, or in other words this is equal to rho m g h by rho m g. Mind you, h is the height at the point 4, that is why I am taking the potential head h here. Okay. So, rho m g plus V 3 square by 2 g. So, these guys get eliminated completely, and we are left with a situation where we have h t times of twice g is equal to again h t equal to h plus V 3 square by 2 g, or in other words V 3 becomes equal to twice g h t minus h whole under the root. So, that is what the gate velocity just prior to the entry, it is just prior to the entry. That means, we are not still entering the mold, but prior to the entry of the mold is actually given by this term V 3 right about here. So, this we can consider to be the gate velocity V g in this particular case. Now, let us go a little further and try to see what happens for the instance shown. So, let us say for the instance that has been shown, the metal level in the mold moves up through a height d h, in a time instance d t. So, I say that the height goes from h to h plus d h, h to h plus d h in time interval d t, while the gate is continuously feeding the metal, and the energy balance equation holds in that particular condition. Let A m be the cross sectional area of the mold, and A g be the cross sectional area of gate. So, you have now that A m times of d h, so that is the area of the mold times of d h equals A g times of V g times of d t. Okay. So, V is the gate velocity, A is the gate area, and d t is the time instance which is there. So, if I assume all this together and put together what happens to let us say if I put the value of gate velocity from the previous equation which I have obtained here into this equation right about this, we get A m times of d h is actually equal to A g times of root 2 g h t minus h d t. Okay. Or in other words, if I just assembled this equation in the right manner, I have d h by root of twice g h t minus h becomes equal to A g by A m d t. So, if we solve this equation, let us call this equation A. If we solve this equation, I should be able to get a relationship for the height versus time, from which I should be able to further find out what is the time of filling of the mold. So, let us say if I just integrate this equation on both sides, 1 by root 2 g is taken common, 0 to the particular height of the mold Hm. Remember, the overall height that would happen by this delta H addition would ultimately this whole height, which is given by height of the mold Hm. So, 0 to Hm dH divided by root of Ht minus H, which is equal to Ag by Am times of, let us say it takes Tf time to fill up the whole mold. So, that the height goes from the existing H value with dH addition all the way to Hm. So, this is how we would integrate, and so the final form that would generate is 1 by root 2 g times of 0 to Hm twice with a minus sign minus twice Ht minus H, that is what comes from the integral, okay, equals Ag by Am times of Tf, or in other words, if I just substitute the limits here, I should have limits of the integration substituted. We have 1 by root 2 g 2 of root Ht minus root of Ht minus Hm equals Ag by Am Tf, or in other words, Tf becomes equal to Am by Ag times of 1 by root 2 g times of twice root of Ht minus root of Ht minus Hm. If the riser is used, then Tf should include the film time of the riser. So, basically this is what the time of filling of the mold is in case of the bottom gating system. So, in both these assumptions, whether it is the vertical or the bottom gating, what we have really assumed is that there is no effect of friction really on changing the velocity head. For example, the velocity at 3 or the gate velocity Vg would be heavily influenced in the real case because of friction which happens between the channel walls or the runner walls and the liquid metal as it moves, you know. So, there would be a higher level assumption that we have to take, and probably a little more higher model which we have to investigate when we talk about what would happen if supposing there is a lot of friction between the metal fluid stream or metal stream and the side walls. Okay. But as of now, this assumption kind of gives a good thumb rule estimation of the total time of filling of the mold, and we will probably go into some numerical problems and try to see how these would vary time wise or value wise if we go from a top gating to a bottom gating system. So, let us say you have these two gating systems which are illustrated in this figure, and I am going to just mention this problem, but probably in the interest of time solve this in a later on module. So, we want to estimate the time of filling of this mold, which is about 50 centimeter into 25 centimeter into 15 centimeter, and the cross sectional area of the gate is given to be 5 centimeters square. So, that is very important here. In one case, the gate is at the bottom of the mold, as can be seen here, and in another case it is at the top of the mold, and we want to see what are the different filling times given you are filling just liquid iron, and so the density etc. can be assumed of the liquid iron, and so we will see if there is really any difference of time between these two different approaches of filling of the mold. So, with this I close on this module, and we will try to solve this problem in the next module. Thank you.